Hi everyone, I'm Yuan, a PhD student of UIUC. Today I'm going to introduce our work. Don't forget the I/O when allocating your LLC. This is a joint work with Intel and University of Kansas. Nowadays, cloud data centers have been virtualized. With the advanced virtualized technologies such as Amazon EC2, Docker Container, and Linux KVM, multiple tenants or applications can consolidate on the same server, sharing hardware resources. This makes the cloud data center more efficient, more scalable, and more flexible. Unfortunately, the benefit of resource sharing is not for free. Tenants may compete with each other for the shared hardware, including cores, cache, memory, and devices. This can lead to severe performance interference. Hence, we need to carefully allocate and isolate hardware resources across tenants. In this work, we focus on the last level cache, or LLC. LLC allocation is not a new problem and has been studied for many years. However, such functionalities didn't appear in the real-world hardware until recently. In 2016, Intel proposed and implemented Resource Director Technology, RDT, on most of its Xeon server CPU lineup. For example, cache monitoring technology, CMT, can let the user know the LLC capacity consumption of a CPU core or application. Cache allocation technology, CAT, enables per core or process LLC allocation in cache rate granularity. Now, we have the weapon to solve the LLC contention between the CPU cores. And the question is, how about I/O? So why I/O matters here? This is because of an Intel architectural innovation called Data Direct I/O, or DDI/O. Conventionally, when transferring data from a device to the host, the DMA destination is the main memory. However, with the development of modern I/O devices, such as 100 GB Ethernet card and high-speed SSD, memory can become the bottleneck in this data path. Hence, DDI/O enables the device to inject data to part of the LLC, bypassing the relatively slow main memory. In other words, now with DDI/O, the LLC and device can talk directly. This also introduces new challenges for LLC management. Here, we discuss two DDI/O related problems. The first is the leaky DMA problem, which has been identified recently by other works. In general, we use in-memory ring buffer as the data structure to let the CPU and high-speed device interact with each other. Also, as I just mentioned, DDI/O will write data to part of the LLC. This LLC portion could be small to only accommodate part of the ring buffer, especially when the packet size is large. As a result, if the core cannot process the data in time, the data can be evicted to the main memory by new data, causing unnecessary memory bandwidth waste. So, how to solve this problem? The rescue work proposed a naive solution by simply using a small ring buffer. However, we argue that this solution does not work all the time. First, there can be many buffers on a single virtualized server for multiple tenants, and the total buffer size can add up to a large value. Second, small buffer size can hurt the performance. We run a simple RFC lossless packet test and sweep the buffer size to illustrate this point. We found that by cutting the buffer size from the default 1K entries to 512, there will be a 13% throughput drop. And if we further shrink the size, the throughput will drop much more significantly. This is because with smaller buffer size, the NIC is more likely to drop packets since there is no available buffer entry. Hence, this motivates us to adaptively allocate more or fewer LLC ways for DDI/O. Use IAT's execution flow. There are 6 major steps in IAT: get tenant info, LLC alloc, pull performance data, status transition, LLC Re-alloc, and sleep. Upon initialization, IAT first learns the tenant information from the scheduler and allocate LLC weights for each of them. Then it periodically pulls the performance data from hardware counters. These values will be compared against those collected in the previous iteration. If the difference exceeds a certain threshold, we move to the state transition step. In state transition step, we determine the system status based on the collected performance data and take corresponding actions in the LLC Re-alloc step. IAT will sleep for a while to let the LLC allocation take effect. The specific interval length is a configurable variable. Regarding the performance metric, we have three. The first two, IPC and LLC ref and miss, is quite common. They basically depict the running status of the applications as well as the memory behavior. The last one, DDIO hit miss, means whether the corresponding cache line is already in the LLC. Here, hit miss, we only need to update the cache line. While miss means we need to allocate a new slot in the LLC for the incoming data. DDIO hit miss reflects the intensity of the I/O traffic and its pressure on the LLC. The core of IAT is a finite state machine. As shown in this diagram, it has 5 states. At initialization, IAT always starts from the low case state. When it detects more DDIO hit and miss, it knows that I/O traffic is more intensive and thus move to the I/O demand state, and will add one more LLC way to DDIO per iteration until the ways reach an upper bound. On the other hand, if it sees more DDIO miss and fewer hit, it knows that the core is pressing the LLC. As a result, it transits to the core demand state and will add more LLC ways for the corresponding cores. To illustrate how IAT reallocates LLC, we use 2 examples. In the first example, we have 1 performance critical tenant and 2 best effort tenants. They are connected to a software virtual switch via virtual I/O, and the virtual switch directly communicates with the physical NIC. Traffic from another traffic generator machine comes from the NIC to the virtual switch and is dispatched to the tenants. In the beginning, we have the following LLC allocation, and the flow count in the traffic is small. Later at T1, we increase the flow count in the incoming traffic. This leads to more space required by the virtual switch since it needs to store more flows in its forwarding table. Hence, IAT enters the core demand state and allocates more ways to the virtual switch's core. At T2, we reduce the flow count, and since there's no need to maintain the big forwarding table, IAT enters the reclaim state and reduce the virtual switch's LLC portion. In the second example, we still have the 3 tenants. However, this time they directly communicate with the physical NIC by hardware virtualization technology. Again, traffic comes from the outside world and is dispatched to its tenant. In the beginning, we have this LLC allocation, and the traffic is not intensive. At T1, we increase the network traffic throughput, and IAT detects it by DDIO hit and miss. Consequently, IAT assigns more LLC to DDIO to make room for the intensive inbound traffic. At T2, the best effort tenant 2 has a working phase change, requiring larger working set. This leads to contention between the core and DDIO for LLC space. IAT then chooses the best effort tenant 1 with a smaller memory footprint to share LLC ways with DDIO to mitigate this contention. Of course, we also have the similar reclaim mechanism as shown at T3. There are also other aspects of our design. Please check our paper for more details. We have implemented and evaluated IAT on real hardware as a user space daemon on Ubuntu 18. The server is equipped with 4 Xeon 6140 CPUs and 2 40GB Ethernet cards. We use both microbenchmarks and real applications to test IAT's effect. Due to the time limit, I will only discuss the microbenchmark results in this talk, including DPDK test PMD, XMEM, and OVS. Also, to reflect the virtualized cloud environment, everything is running in the Docker container. First, we show that IAT can help mitigate the leaky DMA problem. In this experiment, we have two containers running dbdk PMD, which simply forwards packets to the other physical NIC through OVS. We compare multiple results with and without IAT. The first and most straightforward metric is DDIO hit and miss count per second. As shown in these two figures, when the packet size is small, IAT doesn't make any difference since the default LLC portion for DDIO is enough. However, when the packet size is large, IAT is able to reduce DDIO miss by around 30%. This leads to the reduction of memory bandwidth utilization, and finally, the IPC and cycle per packet improvement in the OVS execution. IAT cannot eliminate the DDIO miss. We argue that IAT plus a medium-sized buffer can provide even better performance. We then verify whether IAT can solve the latent container problem. Specifically, we deliberately change XMEM's working set size and DDIO ways to create the problem during the runtime. We have 4 tenant containers, one running the test PMD directly on the NIC. The others are XMEM with different priorities. We demonstrate the LLC miss count on the performance critical container 4. In the beginning, the miss count is low because the container's LLC is completely isolated. At 5th second, since the working set of the container 4 is changed to 10 MB, more LLC miss happens on that. IAT mitigates this by shuffling the LLC weights of container 3 and 4, since container 3 still has a small working size. At the 15th second, we increase DDIO's weight to 4, creating another contention and high LLC miscount. Again, IAT shuffles the LLC allocations to make the isolation of the performance critical tenant. After the 1 second adjustment, the ILC miss of the container returns to a low level. We also measure the XMEM performance in the critical container 4 and found that IAT can let the XMEM achieve around 40% lower latency and 50% higher throughput compared to the IO unaware cache management mechanism. Finally, we evaluate IAT's runtime overhead on a dedicated core. Specifically, we measure its execution time when monitoring different numbers of tenants. Each tenant can occupy 1 or 2 cores. We classify IAT's behavior into stable and unstable. Stable means all time is spent on monitoring, while unstable also includes the time of decision-making and LLC Re-allocation. From the result, we can find that the execution time increases roughly linearly with the number of cores, and the monitoring part is the major overhead. Having that said, the total execution time of a single iteration doesn't exceed 800 microseconds, which is negligible considering its sleep interval. To recap, with the advent of DDIO, high-performance I/O devices have become a critical factor in server's LLC management, bringing in new challenges. In this work, aiming to the leaky DMA problem and the latent container problem, we design IAT mechanism that treats the I/O as the first-class citizen in LLC management. According to the real hardware evaluation, we found that by dynamically tuning DDIO's configuration, IAT is able to mitigate the interference caused by DDIO, offering better performance and isolation. We also open source our enhanced software library with DDIO functionalities to facilitate the future research in the community. Thanks for your listening. Please feel free to contact me for any questions.